Hello everyone, welcome to my channel. This is an educational channel. We look at theories of everything in particular and go deep into them. Today is our 494th video on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson's theory is a system of theory, meaning that it is interconnecting theory of many different subjects. They're all related in their most fundamental nature, and he applies the basic aspects of the theory to as many subjects as he had time to apply it to during his lifetime. He died back in 1990. He was born in 1898. Around 1959, he proposed his two fundamental postulates. This is kind of the key for that he plugged into all these different subjects. He took those two postulates. He arrived at them through a process of induction from an overwhelming amount of data that he accumulated, and turned them into just two sentences about how he believed the universe operated, and then he, through a process of deduction, elaborated those postulates into a theoretical universe. And this theoretical universe was what his universe would look like if his postulates were correct. And then he took time in many of his books to compare his theoretical universe with the measured empirical universe of the legacy scientists. And so that's what we have here in this book in front of me, called Basic Properties of Matter. This book is on chemistry, and Larson arrives at equations for many of the basic properties of matter, like the melting point, for example. And then he plugs his equations into all of the elements and many compounds, and then compares his results with those of the legacy scientists, the mainstream, army of lab coats, and goes through his findings here. We're looking at chapter 15, which is called Electrical Storage. And we had some problems here with this last chapter. First problem is that I do not understand his theory of electricity as well as I understand some other aspects of his theory. Second problem, I don't believe Larson understands the electrical aspect of his theory as well as he understands other aspects of his theory. Another problem is that some of Larson's associates disagree with his application of his theory to electricity in general, and it is a difficult subject. So that's kind of the nature of it. We're trudging through this particular chapter, as we have trudged through a few of these chapters, because this is difficult material, and it's chemistry. But the important thing is that Larson uses the same principles for chemistry that he uses for astronomy, that he uses for economics, that he uses for metaphysics, that you can apply to any subject. And so you want to see how Larson does it. And then once you understand the basic principles of the theory, then you can plug it into whatever subject you want to study and you want to learn about. That's down the line. But first you see how he does it, and you will get the best results with an open mind. If you disagree with him and say, oh, well, that disagrees with something that I already think I know about this subject, then you're probably not going to get anywhere with this. You kind of have to accept Larson at his word and if you're a little bit confused about something or you disagree with something, just let it sit in your mind, and move on to the next part, because sometimes he'll answer his own questions that he presents for you, and clears up any confusion that you might have. And sometimes maybe these things will linger, but you have to kind of give him a hearing. And in order to give him a proper hearing, you really have to kind of hear his theory applied to a few different subjects first, before you can really dismiss him fairly. That's how I see it. And I feel like, at least for me, Mr. Larson has proven that he's onto something. Whether he got everything right, I doubt that. But I do believe that he's definitely onto something, and that he has laid some groundwork that is worth building upon. He recognized that he was subject to error. He believed his theory was correct, but that he didn't necessarily apply his theory correctly in every case. But that if he didn't apply it correctly, that someone would come along in the future, like you or me, and recognize that this is inconsistent with your basic principles, and this is a better solution. So now, if you want to get a rundown of Larson's basic theory, his two fundamental postulates, you want to watch any of my first 474 videos on this subject, where I go into at least a little bit of detail about Larson's approach and his postulates and what they mean and what the ramifications are. And then come back to this video, or you can just wing it and see if you can figure it out right away. Larson's reciprocal system is also known as the universe of motion, because Larson attempts to build his universe upon motion. Everything is made out of motion, not matter and not energy, but motion. And in Larson's world, motion is what you call scalar motion. So scalar motion is a motion that has a magnitude but has no specific direction. You can model scalar motion using a balloon that you put dots on with a magic marker. If you blow up the balloon, all the dots will be moving away from each other. But they won't be moving in any specific direction. They will all just be moving away from each other. Each dot will be moving in every direction away from every other dot. And if you suck in the balloon and contract it, then all the dots will be moving toward each other. And that outward motion Larson calls the progression. The inward motion Larson refers to as gravitation. Those are the two fundamental motions. And then there are many other motions that kind of are built onto that. Manifestation in Larson's universe occurs from basically taking the source, which is that outward motion, the progression, and converting it into that inward motion, which is gravitation, which is goes hand in hand with atoms and aggregates of matter. And for Larson, motion is the relationship between space and time, which sets up a generalized reciprocal relationship, hence the name reciprocal system of theory. Larson's first postulate states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Space and time do not exist in and of themselves. They only exist together in motion. Motion is basically a fraction, with space or time as the numerator and time or space as the denominator. Larson's second postulate is basically the rules that he uses to take his first postulate and turn it into a theoretical universe. And it reads that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. And I disagree with a great deal in that second postulate, but the point is that those are the basic rules of math and geometry that Larson uses to kind of extrapolate his universe, his postulates, into a theoretical universe. Okay, now again, watch one of my first 474 videos to get a longer rundown on the reciprocal system that goes into, discrete units and 3 dimensions and, that kind of stuff. But we're going to start here because we want to turn some pages and get through this work here. And we're in the middle of chapter 15 on electrical storage. Returning now to the question as to the quantities entering into the capacitance, the volt, the unit of force, has the space-time dimensions of T over S squared. In Larson's system, every motion is a fraction, with space or time as the numerator and time or space as the denominator. And all of our scientific quantities, including matter, energy, force, pressure, these are all fractions with space or time as the numerator, time or space as the denominator. In this case, he's talking about force. Force is time over space to the second power, T over S squared. Since capacitance, now he says that capacitance is the units S, electrical capacitance. However, some of his associates have attempted to correct that and claim that capacitance is S to the third power over T. So that's kind of where Larson is running into problems here, is that it seems as if his equations don't work out quite as well as Dave's, who is the person that proposed the S to the third over T. So let's see what happens here. Since capacitance, as we have now seen, has the dimensions of space, or S, the Coulomb, as a product of volts and farads, farad being the unit of capacitance, S, in Larson's system, S to the third over T in the RS2 units, the re-evaluation of the reciprocal system units. The Coulomb, as a product of volts and farads, has the dimensions of T over S squared times S equals T over S. Now, if you did that with S to the third over T instead of S, you would get just the units S, which is space, which is the uncharged electron. In Larson's system, the electron in its fundamental state is uncharged. The electron can be charged, but like everything else in Larson's system, the electron is a motion and the charge is a motion. The electron is a rotating unit of space, uncharged, and it can take a charge, and a charge is a rotational vibration. And so when something is charged, it doesn't mean that it is charged by an electron. It is charged by a rotational vibration. Okay, so there is an uncharged electron and there's a charged electron. And the charged electron is T over S. The uncharged electron is just S. But now Larson is trying to fudge his way through this because he's got the wrong association. And so now he says, but the Coulomb, as the quotient of joules over volts, has the dimensions of T over S times S to the second power over T, which is really T over S divided by T over S squared. And that turns out to be just S. Now, if you did it in the in the other form with just S instead of S T over S, you would get the Dave's units of capacitance, which is S to the third over T, as opposed to S. So now Larson says, thus, and I think thus is definitely the wrong word, because I haven't been convinced of anything that you're saying here. But anyway, thus, the Coulomb that enters into the definition of the farad is not the same Coulomb that enters into the definition of the volt. And you can see that Larson is doing gymnastics here to come up with two Coulombs. There is a Coulomb Q, and then there's a Coulomb with a lowercase q. And they both have different units. Okay, so the farad is not the same Coulomb that enters into the definition of the volt. We will have to revise these definitions for our purposes and say that the farad is 1 Coulomb per volt, that Coulomb being T over S, while the volt is 1 joule per Coulomb, that Coulomb being S. The confusion between quantity S and charge T over S prevails throughout the electrostatic phenomena. Hard to say whether it's coming from the actual historical evolution of this idea, where they don't know the difference between the charged electron and the uncharged electron, or if the confusion is coming from Larson not knowing the difference between the capitalized Coulomb and the lowercase Coulomb, because he attributes the wrong dimensions to the farad, or both. In most cases, this does not result in any numerical errors, because the calculations deal only with electrons, each of which constitutes 1 unit of electric quantity and is capable of taking 1 unit of charge. Thus, the identification of the number of electrons as a number of units of charge instead of a number of units of quantity does not alter the numerical result. However, this substitution does place a roadblock in the way of an understanding of what is actually happening, and many of the relations set forth in the textbooks are incorrect. Now, this is a major thing for Larson in many other aspects of his work, is that when he does apply his corrections, when he does it correctly, many times he does not alter the results of the legacy scientist. He comes up with the same numerical answers, but he comes up with different concepts. It's a different conceptual approach. And in many cases, it leads to the same mathematical results. And so that's what he's saying is happening here. It does place a roadblock in the way of an understanding of what is actually happening. So he thinks that he's correcting this in terms of the concepts, even though it doesn't necessarily show up in the math, because the units are both 1, and 1 times 1 equals 1, and 2 times 1 equals 2. And so when you multiply by 1, nothing really happens. And so you end up getting the same result, but you have a different concept. And so let's see where he goes from here. For instance, the textbooks tell us that E equals capital Q over S to the second power. E, the electric field intensity, is force per unit distance and has the space-time dimensions of T over S squared times 1 over S equals T over S to the third power. The dimensions of Q over S to the second power are T over S times 1 over s to the s squared equals t over s to the third power. Now, here he's using the force per unit distance, the electric field intensity. And so force per unit distance, and the dimensions are q over s squared. So that is t over s times 1 over s squared. Now, if we were using the lowercase q, or in this case, the q that is actually the uncharged electron as opposed to the charged electron, after Larson gets done telling us that the capacitance is uncharged, so he should know that, then we have s times 1 over s to the second power. So that is just 1 over s. Yeah. So we would have 1 over s as opposed to t over s squared, t over s to the third for electric field intensity. This equation is therefore dimensionally correct. It tells us that, as we would expect, the magnitude of the field is determined by the magnitude of the charge. On the other hand, this same textbook gives the equation expressing the force exerted on a charge by the field as F equals capital Q E. The space-time dimensions of this equation are force, T over S squared, equals Q, T over S, in Larson's system, times E, which he just determined that is T over S to the third, but we determined that it was 1 over S. So he says the equation is therefore invalid because his units do not match out, because T over S squared does not equals T over S times T over S to the third power. That would equal T to the second power over over S to the fourth power. Now, if we substituted in S instead of T over S, then it would make sense. Then it would be T over S squared equals T over S squared. But instead, Larson says the equation is therefore invalid. In order to arrive at a dimensional balance, the quantity designated as Q in this equation must have the dimensions of space. Right. So that the equation in space-time form will become T over S equals S times T over S to the third, which is what we just said. In this case, then, the Q term is actually lowercase q, quantity, rather than capital Q, charge. And the applicable relation is actually F equals lowercase q times E. I'm still having trouble kind of understanding what the ramifications of having two Qs are, a charged Q and a space and an uncharged Q, and how that could possibly be a legitimate answer to this question. Okay, we'll go on and see what he has to say. The error due to the use of capital Q instead of lowercase q enters into many of the relations involving capacitance and has introduced considerable confusion into the theory of these processes. Since we have identified the stored energy or capacitor charge as dimensionally equivalent to charge Q, the capacitance equation in its customary form, capital Q equals CV, reduces to time over space, capital Q, equals C, which is S, times V, T over S squared, which is dimensionally consistent. That's because he's using capacitance as S. But if he used capacitance as S to the third over T, which is what Dave says, then we would have S instead of T over S. S equals CV. So again, Dave's version of the farad or capacitance seems to be working better than Larson's. Okay, going on, the conventional form of the energy or work symbol W is equation is W equals capital Q times V, reflecting the definition of the volt as 1 joule per coulomb. If CV is substituted for Q in this equation, as would appear to be justified by the relation Q equals CV, the result is W equals CV squared. This equation is not dimensionally valid, but it and its derivatives can be found throughout the scientific literature. Now let's see, when he derives this, work is simply energy. In Larson's system, energy is T over S. And he says work equals CV. C in Larson's system is T over S, but in the RS2 system, it is simply S. And then V squared is the quantity T over S squared, the quantity squared. So that's T to the fourth over S, T to the second over S to the fourth. And then you have to multiply that by, well, I would think that the C is the farad. So the C actually would be S to the third over T. So that would be, that would end up being T over S. Because, yeah, S to the third over T times T to the second over S to the fourth. So that works out to be T over S, which are the the signature, the units for energy or work. So this equation also works if you're using the farad capacitance as as S to the third over T. But it is not dimensionally consistent if you use Larson's form of capacitance, which is just S. Okay, so let's see how he wiggles out of this. For instance, the development of theory in this area in one current textbook begins with the equation dW equals V dQ for the potential energy of a charge and by means of a series of substitutions of presumably equivalent quantities eventually arrives at an expression for energy in terms of E, the electric field intensity, and AS, the volume occupied by the electric field. The first column of the accompanying tabulation shows the expressions that are equated to energy in the successive steps in this development. As indicated in the second column, the dimensional error in the first equation carries through the entire sequence, and the space-time dimensions of these expressions remain at t to the second over s to the third instead of the correct t over s. And you can see that the difference there is a factor of s squared, t over s squared, which is the same conversion that we have between Dave's farad, s to the third over t, and Larson's farad, which is just s. That is a factor of s squared over t. So again, if you look in Dave's work, he seems to be having a farad that's solving all of these problems, and Larson's farad is only solving the problems where both the farad, both the electron and the unit of charge are 1. And so it works out. I guess we'll kind of get back into this tomorrow when we go. He's got a bunch of equations here, and I think we'll take a look at all of them and show, see how Larson does, and, see what happens. Again, this is one of the glaring errors that I believe that Larson has in his system, and I think this really hijacked a lot of his approach to electricity and makes it a lot more difficult to understand. And maybe I can hide behind that and justify the fact that my understanding of his electrical unit on electricity is very weak, and maybe it's because it's incoherent, but perhaps it's because I just haven't studied hard enough. So it's hard to say, but we'll get into it tomorrow, and we'll try to chop it up and see what comes up. Okay, thanks for tuning in today, and have a